then force on wire placed in magnetic field. So force on wire, which is carrying current placed in a magnetic field. First thing, why the wire experience force when it is placed in a magnetic field? So what is the reason if there is a wire which is carrying the current, that wire experience the force? The reason is, you can see, like example, we have a magnet, the magnetic pole north and south. So north pole is towards, example, right hand side, and south pole is towards the north pole is towards left hand side, and south pole is towards right hand side. So there is a magnetic field of this magnet, which is from north to south. But what happened? There is also a wire which is carrying the current. So as the wire is carrying current, so there is a magnetic field of a wire which is around it, and there is a magnetic field of a magnet which is crossing it, cutting it. So how many magnetic fields are there in this example? The wire which is carrying the current, and there is a permanent magnet. So how many magnetic fields are there? So there are two magnetic, not three, there are two magnetic field. One is the magnetic field of the wire. I'm not saying magnetic field lines, I'm saying how many magnetic fields are there. So there are two magnetic fields. One is the magnetic field of wire, and the second one, the magnetic field of permanent magnet. So whenever there are two magnetic fields, they will always apply force on each other, because, like example, if you have two magnets, you have north south, there's another magnet north and south. So they will repel each other because the like poles are facing, so they repel. How many magnetic fields are there? Two magnetic field. One is due to magnet 1, another one is due to magnet 2. So whenever we have two magnetic fields in the region, they always apply force on each other. So in this case, because we have two magnetic fields in the region, that is why this wire will experience the force. So the answer, why the current carrying conductor, this is conductor, experience force. So what is the reason for that? The two magnetic fields, or when current passes through the wire, it will produce magnetic field which interact with magnetic field of magnet or a permanent magnet. That is why it experience, or the wire, the force. The magnet will also experience the force, but the force on the wire is effect is considerable, because unlike poles are attracting each other, still they have force, because if you have north and south, and south and north. So unlike poles, they're applying forces on each other. That's why they're moving towards each other. If there were no force between them, then they should not move towards each other. Because there is a force, so either attractive or repulsive, two magnetic fields always exert force on each other. So is it clear the idea that why the wire experiences the force? Because there is a magnetic field of a wire and there is a magnetic field of a magnet. That's why the wire is experiencing a force. But how to find this force? How to find the direction of this force? To find the direction of the force, on wire placed in a magnetic field, we will use Fleming's left hand rule. So if you want to find the direction of the force on a wire which is placed in a magnetic field, we will use Fleming's left hand rule. What is the Fleming's left hand rule? According to Fleming's left hand rule, the first finger shows the direction of magnetic field south. The second finger represent the direction of the current, and your thumb will represent or shows the direction of the force. This is called a Fleming's left hand rule. The first finger represents the magnetic field south. How to use a rule I will show. But first finger represents the magnetic field south. The second represents direction of the current, and the thumb is pointing towards the force. So example, you have a magnet is a north pole and south pole. I try to make a 3D so that you understand the pattern easily. And this is how the current is passing. And the question is, state the direction of the force, because as we know that the wire is carrying a current. When the wire is carrying a current in a magnetic field, the wire will experience the force. That is there. But how to find the direction of the force? So for this purpose, to get the direction of the force, we will use Fleming's left hand rule. This is called a Fleming's left hand rule. First thing, all your fingers like thumb, second finger, thumb, first finger, index finger, and the second finger, all should be 90° to each other. First is this thing. Now, according to Fleming's left hand rule, and it is always applicable with the left hand, my first finger should point towards south. So according to the figure which I drew, my first finger should point towards south. So south is towards the right hand side. So my first finger is pointing towards south. My second finger should point in the direction of the current which is coming out or towards me. That's why my second finger is pointing towards me. Where my thumb is pointing automatically. So my first
Sir,
finger.
but this is a straight wire. breaker.
Yeah, the wire is there which is placed in a magnetic field. We are not finding the direction of a magnetic field. We are finding force on the wire which is placed in a magnetic field. So for finding a force on the wire which is placed in a magnetic field, you will use Fleming's left hand rule. So first finger point towards south, your second finger point in the direction of the current. The current is towards me. So my second finger is pointing towards me. Where thumb is pointing automatically, the thumb is pointing up. So what is the direction of the force for this wire? So the direction of the force on this wire will be upward. Is it clear? You can also apply a rule and check that whether it matches with your left hand. It should, because the first way, it always with the left hand. Left hand rule to find. Here we are finding a force on the wire which is placed in a magnetic field. Is it clear? So first finger is pointing towards south. The second finger is pointing towards the direction of the current, and the thumb is pointing towards the force. Now what will happen if I change the north and south, like example, so I change north and south. Now on the right hand side I have south, on the left hand side, sorry, on the left hand side I have south, on the right hand side I have north. And I want to find the direction of the force. The current direction does not change. So in this case, again, the Fleming's first thing, all should be 90-degree. You can see my thumb is 90-degree with my index finger. Index finger is 90-degree with the second finger. All are 90-degree to each other. Now, first finger should point towards south. So my first finger should point towards south. This is my first finger, index finger pointing towards south. My second finger point in the direction of the current. As you can see here in this example, it is pointing outward. So my second finger should not point in, it should point out. So as I rotate my hand, my first finger is pointing towards south. My second finger is pointing towards the direction of the current. Maybe it's not visible, but that's pointing in the direction of the current. So where my thumb is pointing, so my thumb is pointing downward. So in this example, what will happen that it will experience the force. So the direction of the force will be downward. So if I change the direction of the magnetic field or I change the direction of the current, the direction of the force will also change or reverses. Is it clear? The Fleming's left hand rule. So if you want to find magnetic field only of the wire, you will use right hand grip rule. If you use a force on the wire which is placed in a magnetic field, then Fleming's left hand rule, first finger point towards south, second represent direction of the current, and thumb will represent the force or the thrust. Is it clear? Then how we can magnetize an object, like if we want to make a permanent magnet. So methods of magnetization means method of making a magnet. There's electric method. So example, if you want to magnetize an object, initially, if a material is, it's a magnetic material, but maybe its domains are not aligned initially. But domains can be aligned for some material, which we call them magnetic. If it cannot be aligned at all, we call them as non-magnetic. So or initially the domains are not aligned, and we want to make it permanent magnet. We want to align the domains. So what we will do, we will wrap the wire around it. Turn the wire around this material, but it is happening only for magnetic material. Like example, if I use iron, steel, nickel, or cobalt, then it will be magnetized. If I use any non-magnetic materials like aluminum, copper, so it will not work because we cannot align their domains. So this is a wire. The red part is representing a wire, and I'm passing a current through this wire. So as I pass the current through this, what is the effect of this current? What this current will produce? This current will produce magnetic field. We are passing a DC. DC current means that the direction of the current won't change. It will remain same, remain always in one way. So when we pass the current, which rule I will use to find the direction of magnetic field? Left hand or right hand? Right hand grip rule or left hand Fleming's left hand rule to find the direction of magnetic field? So we will use the right hand rule. So when I use the right hand rule here, my fingers will turn in the direction of the current. As you can see, the current is up. I can grip, and thumb is pointing. My fingers are pointing in the direction of the current, gripping it, and thumb is pointing towards the north pole. So this side will appear to be north and this side will be south. And what happened to the domains which are inside? So domains will also be aligned according to the magnetic field. So originally the domains were not aligned, but when we pass the current, the current produces a magnetic field which align the domain. So if we align the domain, this material will behave like a magnet. But this material, if I'm using an iron, iron is also called a soft magnetic material. Why we call iron as a soft magnetic material? Because it can easily lose its magnetization. When I switch off, if I was using an iron, when I switch off, again the domains will be random. But if I use a steel, steel is called a hard magnetic material. So when I stop the current, the domains will remain aligned, so it will remain as a permanent magnet. So if you want to make a temporary magnet or an electromagnet, we use iron here. If you want to make it permanent magnet, then we use steel. So passing a current, aligning the domains, so material will behave like a magnet. But if it is a soft magnetic material, it will only be a magnet or act like a magnet when we are passing a current. The moment we stop the current, the material will be demagnetized, and we call that as a soft magnetic material. If we use steel, which is used to make permanent magnets, so when we pass the current, we are not passing current through the steel, we are passing a current through a wire, and we place this steel within the wire, so it is magnetized due to the magnetic field of the wire. Once we remove this steel, it will behave like a magnet because its domain will remain aligned for a longer period of a time. Is it clear the difference between the hard and the soft magnetic material, and how we can magnetize a magnetic material by passing DC direct current, or which is also known as electrical method? So you can see here in this example, we are passing a current. So if I use a right hand grip rule, this side will be north, this side will be south. So this material will behave same as the direction like a magnet, and it will be magnetized for a longer period of a time. If you are using a steel, it will be a soft magnetic. If you are using iron, then it will be a temporary magnet and only behave like a magnet when we are passing a current and producing a magnetic field. So to make these permanent magnets, we are using steel rather than iron. If we want to make temporary magnet, then we are using iron instead of steel. So this is a solenoid. This is a solenoid. You, there are like many turns, the wire is turned around. So we will pass the current. When we pass the current will produce a magnetic field. So one side will be north and another side will be south. And if the material is placed inside, there's a hollow. So if material is placed inside, that will behave like a magnet. The second method is called stroking. Like when you're stroking by or using a permanent magnet, look, the domains initially are not aligned and you want to make them aligned and you want to make it magnetic. So what you can do, you can take a permanent magnet. So you can take a permanent magnet and rub this many times in one way or one direction. So example, south is there and north. So we will rub this magnet many times on the surface which we want to magnetize. What will happen as this will cause the domains to be aligned because continuously rubbing it, so it causes the domains to be aligned. So once the domains are aligned, the material will behave like a magnet. This is called stroking. And the pole which leave, like example, as I am rubbing, the south pole is leaving. So what pole will be induced? Always opposite pole. So this will be north and this will be south. So rubbing the material, a piece of a material which we want to be magnet, stroke with a permanent magnet. One is a single touch, another one is a divided touch or double touch. So here, when we rub with north pole, so the pole which leave, like example, north pole is leaving, so opposite pole will induce. Here south pole is leaving, so north pole will induce. North pole is leaving, so south pole will induce. So this will produce a stronger, because there's a double touch is there, stronger magnetic field as compared to single touch. So this is the second method to magnetize a material. Then the third method, if you want to magnetize a material, like the first one was by passing DC and the second one is by stroking or rubbing. If you want to demagnetize means if you want to remove the magnetic field. So what we can do, first thing, you should always place in east-west direction. Whenever you're demagnetizing a permanent magnet, you should always place in a east-west direction. Why east-west direction? Because there is earth magnetic field also. So maybe when you are demagnetizing, it might not be demagnetized because of earth magnetic field. So whenever, like this is a compass, north, south, east and west. So whenever you want to demagnetize, you should always place in a east-west direction. So example, I want to demagnetize this magnet. So I should place in east-west direction. North can be on the right or left here in this for a magnet, no difference, but it should always be in east-west direction. Then what I can do, there are domains inside which are aligned because it's a permanent magnet, so the domains are aligned. I want the domains to be random. So if I want domains to be random, what I can do, I can hammer it. So when I hammer, basically I'm deforming it, I'm disturbing the arrangement of the atoms. So it will disturb the alignment of the domains and the material will be demagnetized. This is one way of demagnetizing a material. The second method is by heating it. I can also heat. If I supply heat energy, heat will cause the atoms to vibrate. As the atoms will vibrate, the alignment, the arrangement of the atom will be disturbed and the material will be demagnetize. So either you can hammer it, by hammering you can demagnetize, by heating it you can demagnetize, or there's also another way to demagnetize is by passing AC. So what we will do, like example, we have a material which is a magnet, so domains are arranged or aligned, and we want to disturb the alignment of this domain. So how we can demagnetize? We can either hammer it, we can heat it, or there's also another way. We can use a solenoid and pass AC current through a solenoid, alternating current. Like this is a solenoid, a circular wire. And we are passing an AC current. When we pass an AC current continuously changes the direction of magnetic field, because first right hand side is positive, left hand side is negative. Next moment, left hand side will be positive, right hand side will be negative. So as the direction of the current changes, the direction of the magnetic field will also change. And as the direction of the magnetic field will change, we can gradually take this magnet out. So when we take this magnet out, the material will be demagnetized. Because what happened if the current is passing first in this manner up, so right hand side will be north, left hand side will be south. But if the direction of the current reverses, it's downward, then the right hand side will be north and the left hand side will be south, and this will change continuously. The average 50 times AC changes in 1 second, so it will change many times. And because the magnetic field is changing continuously and we are gradually taking it out or slowly taking it out, so it will reduce the or disturb the alignment of these domains arrangements, and the material will be demagnetized. So there are three ways to demagnetize. One is by alternating current, second one is by heating, and the third one is by hammering. Is it clear? Why we are taking it out from the solenoid? So that some parts of a magnet experience stronger magnetic field and some parts will experience weaker magnetic field. So it will disturb the arrangement of the domains. Is it clear how a magnet can be demagnetized or arrangement of the domains can be disturbed?
Sir, if we made that image straight, turn it 90 degrees clockwise, will there be a difference?
If we use in east-west direct, north-south,
Yeah, not so.
like this,
Yes.
it will not work. Why it will not be effective? Because Earth's magnetic field is there, so it will align according to Earth magnetic field. We want to demagnetize, so whenever you want to demagnetize, it should always be in east-west direction. If you place in north-south direction and you try to heat it or hammer it, but because there is a Earth magnetic field, so the magnet will magnetize according to Earth's magnetic field. So for demagnetization, it should always be in east-west direction. Is it clear?
Yes, sir.
So demagnetizing by heating or hammering, as we discussed. Again, all the cases, east-west direction is important. Then properties of temporary magnets and permanent magnets. Temporary magnets such as iron and permanent magnets such as steel are also known as soft magnetic, steel hard magnetic. It is easy to magnetize and demagnetize, means it can lose its magnetic properties easily. But permanent magnets are difficult to magnetize. But if you magnetize, it will remain magnetized for a longer period of a time. It is used to make electromagnets. It is used to make permanent magnets. What are the uses? Transformer, you will learn transformer in detail. And what are the uses? Your DC motor and AC generator, that you will learn in detail. So this is about the magnetism. Now we'll do some questions related to magnetism. Before that, this application, first some questions. Okay, on this figure, 10.1 and 10.2 shows two view of a vertical wire carrying a current up. So these are the two views. This is, you're looking from the side, and if you look from the top, like if you're looking from the top, this is how it appeared to be. Point P and Q are marked on the card. So there are 2 points which they mark on the card. On the figure, draw a complete magnetic field line through P and indicate the direction. So how I can work out the direction here? So to work out the direction of a magnetic field, I should use right hand grip rule. But I don't have to draw for 10.1, it's mentioned 10.2. So what will be the direction of my thumb? Because thumb represents direction of the
Towards the
current,
current. Towards,
and fingers turn in magnetic field. So as I'm looking from the top, so the thumb should point towards me because the current is going up. So if current is going up, if I'm looking from the top, so it means current is coming towards me. So when I show, if I want to draw the direction of a magnetic field, so my thumb should point towards me and fingers will turn around it. So when I rotate, how the fingers will point? And what will be the direction? Because thumb is pointing, the current is coming out as we see. So fingers will turn around it. So it will be 90-degree, sorry, circular. Is it clear?
yes, sir.
And then draw an arrow, indicate through Q the position of a compass. The compass needle always, because the magnetic field will be around it, so it will be same manner like P. So what will be the compass needle, how it will point? It will point in this manner, because the thumb is pointing current and the fingers are turning around, so it will point towards left hand side. Is it clear? The next part, state the effect on the direction in which the compass Q point. If we increase the current, will it affect the direction? Like as we know, the Q was, the
No,
needle is pointing. Any effect on the direction of the compass
no,
needle?
no.
So there's no change or no effect. And if I reverse the direction of the current, if I change the direction of current, what will happen to the compass needle?
Change.
So it will point in opposite. So here, no change. And at this point, it will be opposite direction as the original. Or you can also say reverse. Direction will not be downwards at Q or F, because the first one, as you can see, when I drew the direction of a magnetic field, so magnetic field is around it. When it is passing through Q. So it was pointing, the compass needle was pointing towards left at this point. If I reverse the direction of the current, then the compass needle will point towards right hand side. The compass needle does not show, okay. The compass needle does not show position of the current. It shows the wire, it shows the direction of the magnetic field due to a current carrying conductor. In the next question, figure 10.3 shows a view from above another vertical. There's another vertical wire, as you can see, which is carrying current up. So there will be magnetic field, and centimeter grid is marked, like you can see. Point W is 1 centimeter vertically. This is 1 centimeter. This one is 1 centimeter. From this one, this wire to R is 1 centimeter, and wire to S is half centimeter. State the magnetic field strength at S, T, and W compared to R. So compared to R, what will be the strength? It will be weaker, same, or stronger?
Oh, okay.
Compared to R, what will be the magnetic field strength at S? Weaker or stronger or same? So S is closer, so it will be stronger. What about T? When we compare,
Same.
it will be same because they have a same distance. So it does not depend on whether it is vertical or horizontal. What about W?
Same.
That will also be same because equally spaced, so same distance. Figure 11.1 shows a flexible wire hanging between the two magnetic poles. The flexible wire is connected to a 12-volt DC that is switched off. That is switched off initially. There is no current. Explain why the wire moves when the current is switched on. So the same reason as I told, when we pass the current through the wire, current is always from positive to negative. So
Force because of magnet.
yeah, the two magnetic fields, the answer, there's how you'll write in terms of like scientific terms, that when current passes through a wire, it produces magnetic field which cuts the magnetic field of permanent or magnet experience force and move. So this is the answer which you should always write. Like, use the term cuts. Cuts here refers to like cross each other. So when current passes through a wire, it produces magnetic field which cuts or interact with the magnetic field of here FIELD of permanent magnet experience force, and that's why it moves. What will be the direction of the force? Which rule I will use here for finding, and let's